But now with his perspective on the current state of play of data-centric engineering and why DCE matters, we're delighted to welcome from Cambridge in England, Professor Lord Robert Mair.
So the underpinning theme of my talk is the vital use of data to understand and improve the performance of our infrastructure. Data comes from measurement, and as Lord Kelvin famously said in 1883, if you cannot measure it, you cannot improve it. The use of data from real performance of infrastructure will enable better decision-making for reducing carbon, increasing resilience, and preserving resources. There is increasing importance being placed on our national infrastructure and its considerable value to society and our economy. Its engineering, management, maintenance, and upgrading all require innovative thinking based on data. Innovative thinking to minimize the use of materials, energy, and labor while still ensuring resilience. National and local infrastructure in the UK need to be fit for purpose for supporting societal development in a changing world, especially in the light of both the COVID-19 crisis and the net zero carbon agenda. There is considerable potential for innovations and new technologies to improve performance and value through reducing construction costs and updating design methodologies. Only with measurement and data can decision makers make step changes in how we design, construct, operate, and maintain our built environment. Without measurement, there is no data. Without data, there is no evidence base on which to make improvements and important engineering advances. Such developments are best achieved by close collaboration between academia and industry. The keynote, the keystone of the philosophy of CSIC at Cambridge, the Centre for Smart Infrastructure and Construction. Next slide, please. So what do we mean by smart infrastructure? Smart infrastructure is the result of combining physical infrastructure with digital infrastructure, providing improved information to enable better decision-making and enabling it to be faster and cheaper. Integrated cyber-physical solutions offer an increasingly cost-effective means of improving outcomes for customers and society. The cost of everything to do with data, harvesting, transmitting, processing, curating, and storing, all continues to reduce, whereas the cost of constructing and maintaining infrastructure keeps going up. Smart infrastructure involves applying this to economic infrastructure for the benefit of all stakeholders. It will allow owners and operators to get more out of what they already have, increasing capacity, increasing efficiency and resilience, and improving services. Next slide, please. There are huge opportunities in combining advanced sensing systems with big data analytics. This is particularly the case for infrastructure. A recent example is the long-term performance monitoring of 2 new bridges constructed by Network Rail in Staffordshire on the West Coast Main Line. Novel fiber optic strain sensors developed by CSIC were installed to measure the detailed performance of the bridges constructed by Laing O'Rourke. Every time a train crosses a bridge, a complete strain pattern is obtained. The monitoring systems on these bridges generate vast amounts of data. CSIC are currently collaborating with the Alan Turing Institute to develop methods of analyzing these rich and important data sets. This project, working with Network Rail, demonstrates the use of real-time data analytics integrated with digital twins to provide valuable information. This information serves 2 vital purposes. It supports engineers and asset managers to schedule safer and proactive maintenance programs. And it optimizes future designs by providing the evidence base for challenging and improving existing design standards and methodologies. This is an example of truly intelligent bridges. Constructing them with integrated fiber optic sensor systems has enabled a degree of advanced sensing and monitoring that previously was not possible. The project has demonstrated the value of developing data-centric engineering solutions for smarter infrastructure. This approach has the potential to transform existing asset management practices, as well as challenging and improving current design practice. It will be invaluable to other bridge owners and points the way forward for the many thousands of bridges throughout the UK. We have simply thousands of old masonry bridges also in the UK. We need to understand through sensing how well they're performing so that we can continue their use with confidence. It's also directly applicable to many other types of infrastructure, whether they be roads, tunnels, bridges, sewers, or flood defences. Data from monitoring and data analytics will undoubtedly lead to improved efficiencies in the design, construction, operation, and maintenance of our infrastructure. It's data that is invaluable. Next slide, please. A digital twin is a realistic digital representation of something physical. What distinguishes a digital twin from any other digital model is its close connection to the model. The concept of digital twins is not new. It is an increasingly common used term in our ever-complex infrastructure and built environment. It's already well advanced in other engineering sectors, especially those undertaking advanced manufacture workflows, where machine-to-machine communication and machine learning technology is used to optimize productivity and enhance levels of automation. Data from sensing devices in the physical asset is pervasively analyzed to monitor condition and optimize efficiency, mostly in real time. In the world of infrastructure, digital relating to three key themes: carbon, resilience of our infrastructure, and prioritization of resources. First, carbon. We have a long way to go in achieving net zero by 2050. We require smart engineering to minimize the use of materials and energy while still ensuring resilience of our infrastructure. Measurement and data will be key to all of this. Second, all new infrastructure we build must be cost-effective and resilient throughout its design life. COVID-19 has forced rapid changes in practice on our society. It demonstrates the opportunity to do things differently. We must not revert to designing and constructing infrastructure in the same way as before. We must apply the latest technologies to find ways of doing more for less, but still ensuring resilience. Digital twins will enable engineers to improve whole life performance, combining data from sensors with innovative changes in design and construction practice, just as engineers do, for example, in the aerospace sector. Third, how should we prioritize our resources? Much of our infrastructure is old, a lot of it Victorian, for example, the masonry bridges I referred to. We should exploit the latest digital and sensing technologies to optimize the assets we already have by measuring and understanding their performance. We should fix them before rushing to build new infrastructure. Next slide, please. In summary, sensors and smart infrastructure deliver value for managing assets throughout their life. This applies to any type of physical infrastructure. They enable full understanding of the performance of infrastructure, both during construction throughout design life. There is huge potential for greater efficiencies in design and performance, and for rational whole life maintenance and asset management strategies. Data is vitally important to maximize efficiency. We need to fully exploit the digital transformation we are witnessing. We need to maximize our engineering ingenuity to reduce carbon, increase resilience, and preserve resources. In conclusion, I hope I've demonstrated the vital importance of data-centric engineering for the future of infrastructure, and indeed for numerous other applications.